For decades, database growth relied on a brute force strategy, known as vertical scaling. When applications demanded more processing power, administrators bought a larger, expensive server. But hardware has physical limits. Eventually, a single motherboard cannot house enough RAM or disk space to manage the relentless volume of global web traffic. The NoSQL movement solved this hardware ceiling through horizontal scaling. Instead of building one massive supercomputer, data distributes across a vast cluster of commodity servers. This introduces a logistical nightmare. Application code is designed to request information quickly. It is not designed to manually track which of 100 different servers holds a specific user profile. If a developer had to manually code for every individual server location, global applications would be too complex to launch. This forces the database software to function as a translation layer, simulating the behavior of a single machine across a landscape of hundreds. To understand how NoSQL systems maintain this illusion, we are going to dissect the architecture layer by layer. We will map the 5 distinct levels of transparency, utilizing MongoDB, Apache Cassandra, and modern mobile edge systems. Without an abstraction layer hiding the raw chaos of distributed computing, operating web applications at a global scale would be impossible. The first bottleneck in any major application is hard drive capacity. A massive dataset of BSON documents will rapidly exceed the physical storage of a single drive. MongoDB handles this using automated horizontal sharding. The database relies on a designated shard key to chop the collection into distinct geographical chunks, spreading the total volume across multiple servers. For applications, this fragmentation is a problem. They need to write records without verifying server locations. The database intercepts these requests using the Mongo's routing interface. This acts as a middleman between the application and physical shards. Working alongside the router are config servers, which house the master directory mapping document IDs to physical shards. The query path is automated. The application sends data to Mongo's checks the config server for coordinates and seamlessly routes the write to server B. This achieves location transparency. The database infrastructure infinitely expands its capacity, while the application interacts with it as if querying a single local drive. Relying on individual shards introduces a fatal flaw. If physical server B suffers a permanent hardware failure, that specific chunk of the database is erased. MongoDB expands shards into single master replica sets, containing one primary and multiple secondary nodes. The application writes only to the primary, which instantly duplicates logs to the secondaries. If the primary crashes, secondaries detect it, hold an automated election, and instantly promote a new primary. For the front-end application, this catastrophic hardware failure registers as just a millisecond delay in response time. No error codes are thrown, and no manual engineering intervention is required. This is replication transparency. Physical servers die and are replaced, but the application remains blissfully unaware that its physical target just changed. Single master architectures excel at consistency, but they have a scaling ceiling. For high-velocity data, like millions of incoming IoT logs, a single primary node physically cannot ingest writes fast enough. Apache Cassandra bypasses this bottleneck using a masterless peer-to-peer architecture. Every node plays an identical role. An application doesn't wait for a primary master. It sends write requests to literally any server in the ring. Removing the master introduces a problem. Servers can't natively know if a peer crashes. Cassandra solves this with the Gossip Communication Protocol, a decentralized system where nodes continuously whisper health data to their neighbors every second. If a server fails, surrounding nodes immediately notice the lack of a heartbeat. They share this failure state across the ring, automatically routing traffic around the dead node without holding an election. Eliminating the primary node altogether achieves failure transparency. It unlocks limitless write speeds with 0 single points of failure. Masterless systems carry a mathematical consequence. Write data in New York and read from Tokyo instantly. You'll retrieve old data. Operating at this scale requires moving away from strict relational ACID compliance toward the base model, basically available, soft state, and eventual consistency. Cassandra exposes this reality through tunable consistency. Under Consistency 1, the database acknowledges the write the millisecond a single node records it, maximizing speed. Under Consistency Quorum, it forces the application to wait for a majority vote, maximizing accuracy over speed. Tunable consistency gives the developer explicit control. It allows them to dictate the trade-off between lightning speed and absolute accuracy, transparently managing the realities of the speed of light. The ultimate extreme of distributed computing moves away from air-conditioned server farms and targets completely disconnected mobile edge devices. Mobile hardware faces high latency, severe battery constraints, and dead zones. Relying on a constant, unbroken connection to a central cloud cluster is functionally impossible. Modern mobile databases, like SQLite or Realm, solve this by running a miniature database directly inside the device's localized RAM constraints. This enables offline capability. Field workers can read, write, and execute complex queries with zero network latency, entirely cut off from the internet. When a connection is restored, the synchronization gateway activates. It intercepts offline queries, manages two-way replication, and compresses data. The gateway natively resolves concurrent write conflicts, mathematically merging them upon reconnection. Edge databases achieve network transparency. They allow the application interface to function perfectly, processing requests as if it never lost connection to the main server. We have constructed a system of massive complexity: shard keys, config servers, replica sets, masterless gossip rings, and synchronization gateways. This labyrinth of technology exists for one exclusive purpose: to shoulder the heavy burden of global networks and hardware decay. It isolates back-end reality from front-end execution, providing pristine simplicity to the application code. Achieving this scale required making specific architectural choices. It meant intentionally abandoning rigid relational schemas and strict ACID guarantees. The NoSQL trade-off is clear. You sacrifice internal simplicity to guarantee distributed survival. Modern database architecture handles petabytes of data by mastering this abstraction, perfectly maintaining the illusion of the single, infinite machine.